Hey everyone, I am going to go through chapter 2.2 with you, covering all the information regarding water. I am going to kind of zip through it, so feel free to pause and um, rewind as needed, okay? So, the first thing is kind of a recap from our previous information regarding chemical bonds and how atoms kind of align with each other. So, we know water is H2O. We should be very comfortable describing that there's two hydrogen atoms and one oxygen atom. And the reason that they have their shape here for our water molecules has to deal with a specific term known as polarity, right? So we remember, hopefully, that oxygen is the electron lover out of these atoms. So it's going to draw the electrons towards it and give itself a more negative charge compared to the hydrogen ions, which are going to, again, unequally share their electrons and give them, towards oxygen a little bit more. So those will be positive. Another more scientific way of talking about it is that oxygen has a higher electronegativity than hydrogen does. So that's why it has that negative um, end to it compared to hydrogen. So that's our polarity piece. Remember that water is made up of polar covalent bonds. So we talked about the polar part, and covalent, like I had referenced already, is the fact that they are sharing their electrons and they're unequally sharing them because it's polar covalent. At any rate, these polar covalent bonds are super strong. That's why water is water in its many forms, right? So it's not going to just break apart with relative ease. It'll likely shift into um, gaseous water vapor, right? Or it might go liquid, or it might go to our ice form. And that all has to deal with these lovely bonds right here that we talked about before, which are our hydrogen bonds. And those are relatively weak, which is why we see them with the dashes. But these hydrogen bonds are going to link up the neighboring water molecules with each other. So we can see the negative end of this one is connected to the positive end of this one over here, right? So the polarity comes into play again. Hydrogen bonds are the key component for all of the main properties of water, which we're going to cover in the next few slides here. So without these hydrogen bonds, we wouldn't have water, which is terrible news for anything that's living because that's a key molecule for life, right? All right. I'm going to cover 4 emergent properties of water. The first, and there will be several different terms that we go through, so feel free to pause and define them as we move along here. But our first property is that hydrogen bonds are the key. So cohesion versus adhesion is the first thing we're going to talk about. Cohesion, the word co means that there's going to be multiple water molecules interacting with each other. So it's how water interacts with other water molecules. When water likes water, that's how we see the water droplets that form when we put them next to each other. And instead of seeing just like a flat surface, they link up together and kind of hold that spherical shape. If you've ever tried to put like a pin or a paper clip and float it on the top of water, that has to deal with surface tension, and that property happens because of cohesion, because water likes other water molecules and creates some sort of film for different objects or like water striders to kind of hang out on top of without breaking the plane, so to speak. Um, so our next term is known as adhesion, and adhesion is referring to water with other things, not itself. So a good example of that, again, would be something like that water strider touching the water. It still is able to cling to something else. Um, but a really key example of this one would be something like transpiration, and that is like the root systems for our plants and how water can travel up and defy gravity and be pulled upward. So, water liking and clinging to other charged surfaces. And another example of this, you might, wipe up a spill of water with a paper towel, and then it might have only used about half of the paper towel, but if you let it sit there for a second, you could see how water like moves all the way across because it likes to cling to itself and then cling to the paper towel and just keep on moving and tracking that way. Um, And then again, that all has to deal with the hydrogen bonds, which is key. I like these photos because it helps us get that visual of the cohesion piece. So we can see the water molecules clinging to each other, forming the droplets. Then we can also see the adhesive pieces going on here with the water clinging to the silk or the spider web. So we have both cohesion, so cute, they're holding hands, and adhesion as they're holding on to that silk on the outside. Another term, like I mentioned before, that I wanted to give you a little more description on is transpiration, and that's a key component that we'll get into later. Really talking kind of about the empirical piece of water potential and why water travels and defies gravity up and out. But there are some really important cells known as xylem tubes in plants that help transport water throughout the entire system. So, water will cling to itself down at the base by the root system, and then it'll start clinging to the roots, adhesion, and start climbing and making its way up through the trunk of a tree and then all the way out through the branches and eventually to the leaves, and it'll evaporate, which looks like this for transpiration. Is also called capillary action whenever water travels up and defies gravity. So if you see that in your reading, capillary action, um, it's more of the process, whereas transpiration is specific for plants. Okay. Another one of the emergent properties is that moderation of temperature is possible because of water's high specific heat. Those of us that have taken science here at the high school before, we've talked about this a ton with chemistry and science 9, but high specific heat is the same thing as like heat capacity. So here's the key here for water. There's a very large amount of energy required in order to change its temperature by just 1 degree, whether that's 1 degree up or down. There's a large amount of money, a large amount of energy that has to be applied in order to make that change happen. Um, so that would be specific heat, and this is important for all of life. Again, thinking about how our aquatic life is going to be surviving based off of this fact, right? So the outside temperature or our terrestrial temperature could increase, get in the 80s, 90s, 100s, but our aquatic temperature or anything related to water is going to be relatively normal or within kind of a regulated range because a very high amount of energy is required to really change a large body of water's temperature by a significant amount. So it keeps our living things safe. Another emergent property is that insulation of bodies of water is done by floating ice. So as I talked about at the very first slide, we can shift from solid to liquid to gas phases of water really easily because of hydrogen bonds. And that solid phase is going to be a key component for keeping organisms and life kind of insulated. So, again, with any other liquid that we might talk about, or the majority of other liquids out there, and when they get to their solid phase, their density increases, which means they sink, right? In our case, for water here, when it reaches its solid phase, the hydrogen bonds actually kind of puff the water molecules outward. So then there's a little more space that goes on, which allows the density to actually um, decrease, and that allows ice to float instead. So that's a really key component. Again, imagine if ice was had a very high or had a higher density compared to its liquid counterpart, it would sink down and crush virtually all of life within our aquatic areas. So that's really important for keeping life safe as we even have our seasons change. Okay, and then this final component has to deal with the fact that water is a really important solvent. Solvent meaning it's a dissolver, or sometimes it's known as a universal solvent. But things that are polar, things that are ions, those are going to interact with water nicely, and they'll dissolve. And then anything else that um, any other categories would go ahead and not dissolve with water. So you'll see the two terms hydrophobic and hydrophilic. Hydrophilic, to break that one down, hydro is water, right? Philic means loving. So hydrophilic is a water loving molecule. So something that dissolves with water. We can think like sugars and salts for hydrophilic substances. And then hydrophobic. Phobic means fearing if you have a phobia, right? So hydrophobic means that you're fearing water. So things like fats and oils would be an example of hydrophobic substances that don't dissolve. Um, and so hydrophilic things, just to kind of go back to that, when they're dissolving other substances, um, it goes through a process known as kind of dissociation, right? So it's going to take our salt ion and eventually kind of like go through and pull away the sodium and the chlorine, the positive and the negative um, charged particles, and separate them out, which allows them to dissolve. So here's our look at that example. Again, it's going to go in there and kind of bust things up and break it apart and go through the dissociation part. So water molecules will surround an ion, which causes it to dissolve. For our next section, we'll talk about acids, bases, and buffers. So again, connecting back to our atoms and molecules and why they interact the way they do. So our first round here, we're just going to kind of take a look at, again, the pH scale to learn about our acids and bases. And why is it called the pH scale? It's talking about the power of hydrogen ions, or the concentrations of hydrogen ions in there. So that's going to determine whether a solution is acidic or basic or neutral even. You may have done this testing before using litmus paper or pH paper, you might call it. But it's basically testing the amount of hydrogen ions within that solution. So this kind of goes through the process in chemistry. You know this like the back of your hand. We don't need to know the general reactions for these or how you would calculate it. So I'm just going to skip on ahead. So how do we know whether we have an acid or a base? Acids are going to have an increase in hydrogen concentration. They're going to be further down on our pH scale over here, and then our bases are going to have less hydrogen ion concentration or be higher up on our scale, and that's where lots of people get confused. Um, but hopefully we remember that numbers lower than 7 are acidic and numbers higher than 7 are basic. And that's just talking about the fluctuations that we can have. Now, most biological components and fluids are going to be within this range of 6 to 8, just to kind of keep things relatively neutral and under control. Once we hit those acids and bases, it can be a little tricky for our cells to be able to survive that way. So that's just one key component there. I want to make sure I don't forget anything that I wanted to reference in there. Um, but another visual for you. So we can see the increase and the decrease in hydrogen ions as we go along. So here's our neutral ones with equal amounts of hydrogen and hydroxide. So some people might reference basic solutions as having more hydroxide ions. We'll talk about what hydroxide is a little bit more in our next section as we talk about functional groups. But anyway, it could be any negatively charged, solution that is added in there. It's not necessarily hydroxide. That could lead to a basic solution causing less hydrogen ions in there. So you really should just focus on the hydrogen piece. And then we can see over here with our S acids that there is a greater concentration of hydrogen. But so here's that pH scale. The question becomes like, well, how is it possible that we have our stomach acid, right? That's super acidic, but we have stomach cells that live there. How is it that they survive? Well, honestly, they don't really survive that long. It's like every couple hours, sometimes, 20, 30 minutes that they're regenerating in there. So being within an acidic environment is difficult for our cells because, as I referenced before, the majority of them lie within this neutral range here. Um, and that same thing goes like, what if you're drinking, tomato juice, or you have Coca-Cola and you take that in? Does that affect our cells? Yes, it does, right? You're adding in an acidic environment for those cells, but we have something known as biological buffers, which kind of help balance things out. So I'll talk about that next. But buffers are going to be really important for life's survival here. We know that's important. Okay, so buffers are going to be found within biological systems and within our cells to just kind of keep things in check and balance. So, as acids or bases are added to the environment or added to the cellular area, these will help kind of keep things at a neutral stance, which is super important. So, again, we've got our blood pH level, which is stable around 7.4. So, that's really key. If it goes beyond 7, like lower than 7, sorry, or higher than 7.8, that leads to death. So, we need to have a system in place that can really keep it within that range or cycle it out really quickly so that the blood pH level is within that range. So we have one, which is the bicarbonate system or carbonic acid, which will go through and, draw out the carbon dioxide from our blood plasma, which is a key thing. And it does it really, really quickly, like one of the fastest reactions that I've ever heard of. And that's important, right? We don't want carbon dioxide flooding our blood plasma systems. So that's one example of a buffer. The same sort of system applies to like coral reefs and how those have been greatly impacted by pollution and carbon pieces and things like that. So that bicarbonate system allows our coral reefs to stay intact. And again, if it gets beyond that pH range, that's where they die off, and they have been decreasing because of the amount of carbon. Again, humans constantly polluting different systems. It has to deal with that. What's another example of a buffer or something else that we have when, if you ever, have acid reflux and you take an acid, that would be an example of a biological buffer, something that's going to help kind of regulate that internal system and help maintain homeostasis for all of life. So that should cover our buffers. We'll eventually be going through and looking at, again, those functional groups. We'll look at what pH and buffer scales look like. And you're going to be doing a little practice essay on water. So hopefully you know those properties like the back of your hand. See you soon.